In this section, we're going to be looking at hypothesis testing and confidence intervals again, except this time instead of two proportions, we're going to be looking at two means, in the particular case where the two means are independent of each other. Let's go ahead and look at a couple of examples and a definition of what independence means in this case, and then we'll also look at a definition of matched pairs. So when we talk about independent, what we're referring to is basically how two populations are separated and how individuals are selected from each population. So in this case, independent means the individuals collected from one sample So again, the individuals selected from one sample do not dictate or have any influence on which individuals are selected from the next sample. So that's the definition of independence that we'll be using. Now when we talk about this definition of independence, remember it's always referring back to the individual selected, and these could be people, these could be samples of rocks or samples of some chemicals or animals. So when we say individuals, we just basically means the thing that's being sampled. So if I know what sampling from one sample is, that doesn't influence how I'm going to be sampling from the second sample. We also have some examples of matched pairs design. Matched pairs are easy to spot. Basically, for a matched pairs design, just the opposite is true. I match a pair from the individual sample from the first sample, and that helps me to determine the individuals that will be selected in the second sample. So the individuals selected to be in one sample are used to determine the individuals to be in the second sample. So if we were looking at, let's say, a homeowner and their pet, and we were looking at something, let's say about blood pressure of the homeowner and blood pressure of the pet, because I randomly selected a homeowner, that automatically tells me that I'm going to be working with their pet in the second sample. So that's why it's called matched pairs, because they'll actually match together. Whereas independent, again, they have no connection and they're considered separately. But what we're going to be doing in this particular section is we're going to be working with this idea of independence. Now, when we're talking about this idea of independence, we're still working with hypothesis testing, and we're also working with the two-sided confidence intervals. So all of our hypotheses are the same, and then from there I can go start talking about assumptions and then the types of formulas that we'll be using. So again, we still have HO versus HA. Now because we're looking at two means, we're looking at the difference. mu1 minus mu2 equals 0. Remember, equals always goes with the null hypothesis. And for my alternative hypothesis, one thing I could have is mu1 minus mu2 is less than 0. Now remember, for this particular case, mu1 minus mu2 equals 0. I could add the mu2 across, and this is the case of equality. Here, when I have mu1 minus mu2 is less than 0, I'd add the mu2 across, and I have mu1 is less than mu2. So this is actually checking to see if the first mean is less than the second mean, statistically less. So we have to kind of keep track of what this difference is meaning. We can also look at another null and alternative hypothesis set. We could look at HO versus HA, mu1 minus mu2. The equality goes with the null hypothesis. In this case, let's go ahead and look at greater than 0. So again, no change here. Mu1 minus mu2 equals 0. I'd add the mu2 across and I'd get mu1 equals mu2. Okay, here in this case I'd have mu1 minus mu2 is greater than 0. When I add the mu2 across, I get mu1 greater than mu2. So this is checking to see if the population mean for the first group is greater than the population mean for the second group. Now our third case is always the interesting case because we're looking at basically the confidence interval as well. So here we have mu1 minus mu2 equals 0. Mu1 minus mu2 does not equal 0. So here we're saying it's different. It may be greater than, it may be less than. I don't know which direction, I'm just saying that it's different. So again, as above, mu1 minus mu2 equals 0. Add mu2 across and I get mu1 equals mu2. Mu1 minus mu2 does not equal 0. Add the mu2 across and I just say, you know what? They're not the same. They're different somehow. The two means are different. Now this also is related to a confidence interval. So this is the test that's related to the confidence interval. So whenever you're asked to create a confidence interval here, it's always good to go back and think about what the null hypothesis is saying. Now we also have a few other things that we need to do here. We need to determine which formulas I should use and when. So when I'm talking about inference, about two independent means, I have two assumptions that can be made. And based on which one of these assumptions I choose, I'll choose a different set of formulas. Okay, so for our first one, let's go ahead and assume that population standard deviations are the same. And now if this is the assumption, we're going to use the pooled standard error. Now there's a lot of formulas that are going to go with this, and you can certainly do these by hand, but I'd really encourage you to start learning how to use the stat button on your calculator under tests to make sure that you have the correct values. Now if we use the pooled standard error, I have a test statistic, and my test statistic is t because sigma is unknown, and it's x bar 1 minus x bar 2 minus mu1 minus mu2, and that's usually 0 because my hypothesized means for my null hypothesis, mu1 minus mu2 is 0. And this is divided by my pooled variance, and that's s squared p over n1 plus s squared p over n2. And this is all square rooted, numerator and denominator. Now this is going to be distributed with t degrees of freedom, and the degrees of freedom will be equal to n1 plus n2 minus 2. So instead of just n minus 1 degrees of freedom, I pool the sample sizes and subtract 2 for my degrees of freedom. Now the question is, what is this s squared p? Well, before we get into s squared p, let's go ahead and look at a confidence interval as well. So a confidence interval always has point estimate plus or minus margin of error. In this case, x bar 1 minus x bar 2 is my point estimate, plus or minus t, alpha over 2, with particular degrees of freedom. And we'll talk about those in a second. S squared p over n1 plus s squared p over n2. Now in this particular case, my degrees of freedom are the same as above, n1 plus n2 minus 2. So add the sample sizes together and subtract 2. Now, the formula for s squared p, this is why we want to use our calculators. This one can get a little bit ugly. So s squared p is the sample size of this first group minus 1, s sub 1 squared, plus the sample size of my second group minus 1, the standard deviation of the second group squared, s sub 2 squared, all over n1 minus 1, plus n2 minus 1. Now you could also write this as n1 plus n2 minus 2. but we like to write it like this because it matches the N1 minus 1 and the N2 minus 1. So this is my pooled standard, this is my pooled variance, and basically what ends up happening is I use these formulas when I can assume that the population standard deviations are the same. Now what do I do if I can't assume that they're the same? So this is my second case. So here we would assume the population standard deviations are not the same, so I have not equal to in this case. Well, it actually makes our formulas a little shorter. So here my test statistic is still going to be a t. The numerator is the same, x bar 1 minus x bar 2 minus my difference of my hypothesized means, mu 1 minus mu 2. So this is s sub 1 squared over my sample size, s sub 2 squared over my sample size for group 2. I don't have the pooled mean anymore. Now my degrees of freedom are kind of interesting here. This is going to be distributed t degrees of freedom, where degrees of freedom is the smaller of n1 minus 1 or n2 minus 1. So I calculate both of these, and whichever one is smaller I would use for my degrees of freedom up here. Now I also have a confidence interval for this particular situation. So for my confidence interval, I'll have x bar 1 minus x bar 2 plus or minus t alpha over 2 with some degrees of freedom which match the same up here. And then I have s1 squared over n1, s2 squared over n2. Now here my degrees of freedom are equal to the smaller, as above, of n1 minus 1 or n2 minus 1. So everything's the same here really. We're still talking about confidence intervals, we're still talking about test statistics, we're still talking about p-values and the steps that we use for testing a hypothesis. The only thing that's really changed here are the formulas, whether I'm using a test statistic for assuming the standard deviations are equal or not equal. So that's the first thing we need to do, is decide which formula to use when. So let's go ahead and look at our first example. For this example, we're going to be looking at car payments and two different groups, foreign and domestic. So before we go ahead and get started here, for this problem, we want to go ahead and assume that the population standard deviations are equal. So right away, let's go ahead and assume sigma 1 equals sigma 2. Okay? Now here, for our foreign cars, we do a random sample of foreign cars and we look at the car payments, and we see that for the foreign cars we have 50 people that we selected, and for those 50 people we found that their average car payment was $772.80, and the standard deviation was $15.90, 15.9. Now if we wanted to keep track of this, we could call this n sub f for foreign, x bar sub f for foreign, and s sub f for foreign. It just kind of helps us keep track. Now we also have domestic. So for domestic, my sample size in this particular case, let's say, was 50, and the average car payment for the 50 randomly selected people who own domestic cars is $593.50 per month, and the standard deviation is going to be $11.10. Now I'm going to use a sub D for domestic. Now a lot of times they'll just say n sub 1 and n sub 2, and it's kind of hard to keep track, so that's why I kind of prefer to use the subscript to help me keep track of something that has to do with the population, like F and D for foreign and domestic. So we're going to go ahead and run a full-blown hypothesis test on this, and we're going to use our calculators to help us summarize these values. So up here, before we get started, if we assume sigma 1 equals sigma 2, this is not pooled. This is not a pooled standard error. we use the pooled standard error when they're not equal. Okay, and I have this notation wrong, so let's make sure we fix this. Here, when we have assume sigma 1, let's make sure we have does not equal sigma 2. So then we're not using the pooled standard error. So this should be not equal to. And we have the same summary values. Now let's go ahead and get started with our hypothesis test. In this particular case, we were trying to determine if there was a difference in car payments between the foreign and the domestic group. Now we can clearly see that there is a difference, but the question is it statistically significant difference or not? So what we want to do is we want to check and see if the average car payment for the domestic car purchasers are statistically significantly lower than that of the foreign. Now remember, what we want to start with here then is the difference, mu1 minus mu2. Equals is always in my first case for my null hypothesis equal to 0. And then my alternative hypothesis would be mu1 minus mu2. And again, I should be careful here. I'm not going to use mu1 and mu2. I want to use foreign and domestic. So let's go ahead and look at the difference. Let's use domestic and foreign here to help keep track. So the difference between the mean of the domestic minus the mean of the foreign is going to be less than 0. Now remember, there's another way that we can write this. This would be the same as mu d less than mu f. So I'm looking to see if the average domestic payment is less than the average foreign payment, and that's where this difference comes into play. Now you can see this alternative hypothesis written as the difference or just with the less than. It's good to note what this actually means over here. Step 2, let's go ahead and use a significance level of 0.01. Let's go ahead and calculate our test statistic next. Now this is when we're going to use our calculator to help us out. Now if you want to do this by hand, you absolutely can, and you'll just go ahead and follow through with the non-pooled estimate for our test statistic. You'll use s sub 1 squared and s sub 2 squared. Let's go ahead and open up our calculators to see how we can use this to help us calculate these values. So we go to Stat, arrow over to Tests, and we are looking at a 2-sample. So we want to look under these cases. 2-sample, and it looks like we have a t-test here. So 2-sample t-test. Because I am using a t-distribution because I do not know sigma 1 or 2, I'm just assuming they're equal. Okay, now our first option here, if I have 2 columns of data, it would just pull in the information from my columns, or under stats, what I would do is I just enter my data. So let's go ahead and enter the data. We're going to enter the information from foreign and domestic. I'm going to enter the domestic first because it's my first value listed here. So x sub d is 593.50. S sub x is going to be 11.10. Sample size was 50 for my first domestic group. X bar of my foreign group will be 772.80. The standard deviation will be 15.90. Sample size is still 50, and then I have to look at which direction of my test that I'm looking at. So I'm looking at mu d minus mu f less than 0. So let's go ahead and go over to the less than case here. Now this pooled is where I have to decide if I'm using the pooled or not, and we can see from my notes here sigma 1 does not equal sigma 2, so we do not use pooled. So we want to make sure this says no. And we don't really care about our curve sketch, we just want to go ahead and calculate. And this gives me quite a bit of information here. It gives me sample size, it gives me means, standard deviations that I entered, but the most important stuff is right here at the top. So let's take a screen snip of this and pull it into the lecture. So we can see from this information that's given that this is my test statistic. Now this is some crazy big test statistic. We usually don't see anything this big. But for this particular case, we have t equals negative 65.38. That's a huge test statistic. Step 4, we'll have our p-value. Now I don't have to calculate the p-value. It's given right here. The p-value here is essentially equal to 0. Next, we'll go ahead and make a decision. Remember, there's two decisions I can make. I can reject HO if P is less than or equal to alpha, or I can fail to reject HO if P is greater than alpha. Well, in our case, P was essentially equal to 0. Alpha was 0.01. We can see pretty clearly here that P is less than or equal to alpha. Therefore, we would reject HO. So next step, we'll have a summary. Okay, now for the summary here, we want to make some sort of a conclusion. Now we decided that we were going to reject HO. So again, we blame it on the data. The data supports the conclusion. That the average car payment for a domestic car owner is less than that of a foreign car owner. Okay, because if we rejected HO, what that's saying then is we have evidence to support this alternative, and this says the average of the domestic payments is less than that of the foreign payments. So again, being able to use your calculator for this is a huge help, and you can focus in on the decision and the summary then, and not so much on the heavy calculations. Let's go ahead and try another problem. For this example, we're going to go ahead and start with the same beginning. We are going to assume that the population standard deviations are not equal. So sigma 1 does not equal sigma 2. So to get started, we're not using pooled. And that's usually the first determination we need to make. Now in this case, we're going to be working with a confidence interval. And what we're doing is we're looking at some information about people and whether they're colorblind or not. And then we're also looking at their brain volumes to see if there's a relationship between brain volumes and colorblindness. So let's go ahead and look at two groups. Our first group is colorblind, and our second group is not colorblind. So our first group, we have a sample of size 10. So I'm going to call this NC for colorblind, sample of size 10. The average here for this particular group is going to be 0.32. And that's going to be X bar sub C for colorblind. And then we'll also have the standard deviation of the colorblind group, and that's going to be equal to 0.92. Okay, so again, that's for the colorblind group. Now for the not colorblind, I'm going to call that N sub N. We still have a sample of size 10. The average for this group is going to be 0.48, and the standard deviation of the not colorblind group is going to be 0.92. Now what we're weighing here are brain volumes. So the average brain volume, standard deviation of brain volume, and standard deviation of brain volume. Well, what we want to do here is we want to go ahead and find a 99% confidence interval. And I want to use this 99% confidence interval to determine if there's a difference between brain volumes for colorblind and not colorblind people. So basically the null and the alternative hypothesis that we're going after here, again, mu and mu, I'm going to do colorblind minus not colorblind equals 0. Colorblind minus not colorblind does not equal 0. Confidence interval is related to a two-tailed test. Okay, so this is really what I'm getting after. So to construct our confidence interval, you can go through and go point estimate plus or minus margin of error and use the formulas that we have before. Or again, it's a good idea to start getting used to using your calculator for some of these calculations. So we'd start with stat, arrow over to tests, and we want a confidence interval. So go ahead and scroll through. Here's intervals. So this looks like a 2 proportion. We don't want proportion, so let's keep going. Here's 2 sample t interval, so I think that's what we need. So again, data would be if I had my data in columns, and there's one of the problems in the homework set that talks about the ratings of different movies. So there's R, PG, PG-13 movies, and then you're asked to compare how much money they make in millions of dollars. And so that's probably where you'll want to put your data into some lists and work from there. And then for our case, we have X bar 1 and X bar 2. Let me go ahead and scroll up here a little bit. So for X bar 1, that's going to be colorblind. That's because that's my first value that's listed here. It's going to be 0.32. Let me see if I can scoot this up. 0.32. Okay, standard deviation is 0.92. And sample size is 10. X bar 2 is 0.48. Standard deviation is 0.92. Sample size here is 10 as well. Now my confidence level was 99%, that was given. So I'd have 0.99 here. It's not pooled, so I'm going to stick with no here. And I want to go ahead and just calculate my confidence interval. Now once I have this confidence interval, then I can answer some questions about my null and my alternative hypothesis. So my confidence interval looks like it goes from negative to positive values. So my confidence interval goes from negative 1.344, and this is talking about the difference, less than the difference in the means, mu sub colorblind minus the average of the not colorblind, less than 1.0243. Now, because 0 is in this interval, meaning the difference could be negative, 0, or positive, so because 0 is in the interval, basically what that says then, in terms of this hypothesis right here, is that this could be true. Mu c, the average of the colorblind minus the average of the not colorblind, could be equal to 0. So basically I would fail to reject HO. Okay? So if we had to draw a conclusion here, does this suggest that the population means are different? So the data supports the conclusion that there is no difference in average brain volumes between colorblind and non-colorblind people. Because remember, 0 is in the interval. So it's good to get used to drawing these conclusions, comparing the differences between a hypothesis test and a confidence interval. And remember, a two-sided hypothesis test, a two-tailed hypothesis test, will yield the same result as a confidence interval as long as the level of confidence and the value of alpha is the same for both of them. For our next example, we're going to go ahead and start with a different assumption. Here we're going to assume that sigma 1 and sigma 2 are the same. Their population standard deviations are the same. So what I want to do here is I want to use the pooled standard error. Before we didn't, now we will. So again, you can follow through with all the calculations by hand. You can use your tables, but I want to focus in on using your calculators to kind of get around making mistakes with the handwork, since the formulas are getting pretty complicated. So let's go ahead and look at our two populations. So this has two groups. Our first group would be a low protein diet for young children, and their second group would be a high protein diet for young children. And what we're going to be looking at to see if there's a difference in growth rates for these two groups. So for the low protein group, we have a simple random sample of 45 children. So N sub L, low is my subscript there, is 45 children. The average growth in a month for this group would be 0.96 centimeters. And the standard deviation for this low protein group would have a standard deviation of 1.25 centimeters. Now for my high protein group, I'm going to call this N sub H for high protein. The average was, average is over here. The average was 1.11 centimeters, and our standard deviation in this group was 1.11 standard deviations as well. Okay, so the mean and the standard deviation was the same here. Now, the sample size for this group is the same. It's 45. Now we want to go ahead and test the claim, and we'll talk about the claim here in a little bit, at the 5% level of significance. So we want to test the claim at the 5% level of significance. HO versus HA. We want to just check to see if there's any difference in the means at all. So mu sub 1 minus mu sub 2 equals 0. But again, it makes it easier to keep track if we think low and high. So low protein minus high protein. Now, if we want to see if there's any change at all, what we would do is we would call this the not equal to case. And remember, if we move the mu sub H over, this would be the same as mu sub L equals mu sub H. Now our level of significance would be alpha is 5%. And then we'll go ahead and find our test statistic, and we're going to be using some of the features on the calculator to help us with that. So we'll go ahead and find the test statistic. It's going to be a t-value. And then we'll find our p-value and stuff from there. So we would go under stat, tests, and we are looking at a two-sample t-test. So on my calculator, that's option 4. It might be different on yours, so just look for the wording two-sample t-test. Now what's changing on this one is I have a pooled estimate now. So first of all, I'm entering my data, so I choose stats. If you have your data in columns, your raw data, you could choose data here. And if I chose data, what would happen is they would ask me for some other information here. They would say, okay, what's your list 1 and 2, etc. But we don't have raw data, we have summary statistics. So for my L values, for my low values, that would be 0.96 for my average. Oops, let's be careful how I enter that. It's 0.96. My standard deviation is 1.25. My sample size is 45. X bar 2, which is my average of my high protein diet, is 1.11. The standard deviation is 1.11. My sample size here is 45 as well. And on this one, I'm looking at the not equal to case. I'm just looking to see if there's a difference. Now under my pooled estimate, remember I'm saying yes now because I'm going to assume that the population standard deviations are equivalent or equal. So I want to have a yes here. And let's go ahead and hit calculate. And this will give me my test statistic and my p-values. So let's go ahead and copy this into the lecture. So for this case, it looks like my t is this value right here. This is my test statistic. It's negative 0.6019. And again, that's my test statistic. And you can go through and calculate that by hand as well. But I think it's just as easy to use this to get accurate values, because there are a lot of mistakes that can be made when you're calculating those with those complicated formulas. Now my p-value here, again, you can calculate that or you can just get it directly from our output here. 0.5488, we'll say rounded to 4 places. Next, I need to make a decision. I can make one of two decisions. I can reject or fail to reject HO. I'll reject HO if P is less than or equal to alpha, and I'll fail to reject HO if P is greater than alpha. So again, P in this case is equal to 0.5488. That's a very big p-value. My alpha was 0.05 that was given. I can see pretty clearly here that P is greater than alpha, therefore I'd fail to reject HO. So if I fail to reject HO, that means I have support that they're equal, that the two averages are equal. So again, I'm looking at a low protein diet and a high protein diet, and I'm looking at the difference in their growth. And what this is saying is it doesn't look like there's a statistically significant in the average growth rate based on the diet. So that would be part 6 here would be my summary. So again, the data supports the conclusion. That there is no difference in average growth per month between the two diets. The low protein and the high protein diet. So again, these are the types of conclusions you'll want to be able to come up with and write. Because we're using our so much for calculating the values, that means we need to focus a little bit more on the process that we're going through here and the decision and the summary values. Now again, when we're working through these problems, you need to make sure you look to see whether we use a pooled estimate of the standard error or not. It's usually pretty clearly written in the problem. So start with that and then fill in your values from there about whether you're using a hypothesis test or a confidence interval. Either way, it's a good idea to always write your HO and HA before you get started. As usual, if you have any questions, please let me know. Bring your questions to class, stop by my office, or the Math Center is open as well. Good luck.